Welcome everyone to my final project presentation for my sharing of implementation of generative and adversarial network and results. The purpose of the project is to gain experience from building GAN, DC GAN, C-GAN, understand the methodology researchers, industry has tried to overcome problems by deep networks, so I will be able to further explore different GANs evolved. My work based on the first version of GAN published by Ian Goodfellow in 2014, which proposed chaining to our serial network at the same time. With the huge success of GANs keep on evolving, and DC GAN was proposed to address a couple issues of GAN. Firstly, in contrast to what we learned in Project 5, GAN is purely fully connected network, so there's no convolutional layers. It is well known as difficult to train as well. DC GAN is proposed to use convolutional layers, such that filters could be visualized and specified. It is also proposed to use batch norm and leaky loop to address training stability problem. For both GANs, the generation of images is completely random, meaning I can't actually control which class or label of an image I want to generate. Therefore, conditional GAN comes up with the idea of matching the results, also taking a label into consideration. For the general outline on the solution, I used mixed handwritten digit datasets to train GAN, DC GAN, C GAN at the first place. After the networks have become stable, I fed RGB images from the CIFAR dataset to the DC GAN. I thought it should be a correct approach after I'm sure every steps were correctly set up, but then I ran into a couple issues. One is computational time, and I have to switch my gear to Google Colab for better GPU resources. So now we have real images, either from mixed CIFAR10 datasets, pass them into a discriminator, then discriminator is a classifier to know if it is a tensor from a real image, or it doesn't close to real image at all. So it is able to come up with a loss function, and it will then be able to backpropagate to learn better for what is real or generated images. On the other hand, there's a generator network. They are trying to compete with each other for the results they desire, but in an opposite way. Now, after discriminator returns an error function, the backpropagation of generator allows it to generate an image next time better and with less error calculated. For C-GAN, it is the same idea, but this time we also pass a label. So if we record what we have done in Project 5, it is the ground truth label from the mixed dataset. Likewise, for generator, we pass a latent vector together with a random integer. So at the end, discriminator has to also take the label into account when classifying. Meaning, even though a real picture is computed, if the labels are not matching, it will still be regarded as a non-real image. So this is the network infrastructure I have built for the GAN. So for GAN, we can see that for both discriminator and generator, they are all fully connected layers, and there are no convolution layers involved. For DC GAN, the structure of discriminator looks the same as what we did in Project 5. After all, it is a classifier. Now, at the generator, transposed convolution layer is new to me. So refer to the diagram here. When a single column latent vector is passed to a generator, each layer upsample the tensor until it becomes the dimension of an image size we want. So the result of GAN is satisfactory. From epoch 0, which I would say is a procedure we shouldn't have missed as a control test, and I will explain further at the last slide, shows a purely random image generated. After 20 epoch, I start to see some patterns. Maybe barely can see it as a digit. And then at epoch 60, I start to see the shape of digits clearer until epoch 200 at the best. So for DC GAN, I test with epoch 20 for the first trial. At first, it amazed me because it could achieve much faster computation than GAN from the surface, because it is the same epoch evaluation. And then if you compare it with the previous GAN result, it is obviously much better for the same epoch. Then at epoch 100, it is even photorealistic. I can tell these images are generated or from the MIST database, versus the images from GAN at the epoch 200. The digits could clearly be seen, but there are so much paper noise by GAN. So another point to look at this term is I also observed mode collapse with DC GAN. So mode collapse is a phenomenon when a generator reaches a point that it learns to generate one or just few images and able to pass discriminator. So literally, we start to see same image generated for the whole data set instead of random digits or images. So for the result of CGAN, I can see most of the images. For example, 652 are generated with correct labels, or digit 3, which looks actually pretty close to the label. So lastly, for CIFAR, I can get satisfactory results from DC GAN. So for experiment with GAN, I have tried to experiment with lantern size 144 and 400, batch size 1632 128, but I don't see significant difference. One of the reasons could be because I'm using a simpler dataset MIST. Maybe it could be helping with higher resolution images or RGB images. For the experiment of batch normalization at epoch 20, I thought it could help a lot, but then even when the training continues to go on, the result doesn't change. So it seems to me at epoch 20, it has stopped the optimal training already. For the findings, mode collapse was found quite often when the epochs keep going. Then for computational challenge, having said that the DC GAN shows much better quality of images for the same epoch of GAN, but in fact, each epoch takes much longer time than GAN. So better quality is in the expense of computation. Then when I try to fit RGB into DC GAN, the longest running time I have experienced was 4.5 hours for a 16 batch size, 100 epoch training, and unfortunately, the result came up has issues, and I have to switch to Google Colab platform for sure for better performance. Then the same training took 1.5 hours to finish. Lastly, the IM show command gave me some hard challenges. If we look at the generated image at epoch 1, it was shown as grayscale. It's still obvious as a display problem, but then when I fix it with a NP transpose, as shown here, it seems you can learn something, but just the contrast is weird. So I have to give it up to fix because each training takes me so long time. But just before the day of submission, I got a little luck to give it the last try of Google search to see if I can find a solution. And finally, the best to use to show an image generated by a generator is by the PyTorch transforms, and it solved my problem. I hope everyone enjoyed the journey and the semester. Thank you for watching and all the best.